Yeah. So we are going to see LTSPICE simulation for differential amplifier. And so you studied as a differential amplifier in your labs, I think. So you people have studied this amplifier. Did you study normal amplifier, the BJT amplifier or MOSFET amplifier? Yes, students. Okay, so your basic differential MOSFET pair configuration look like this. Okay, and you are aware of there are two MOSFET. Okay, generally your single MOSFET amplifier generally, okay, it look like this. Okay, you have one input voltage and then there is one RD and there is a DC biasing VDD, and you apply you assume that, like, you can assume that your gate is biased and you apply input voltage here. Okay, so what we do is we actually bring uh, so yeah, this is a single ended signal, and then what we do is we actually bring two MOSFET together. Okay, two MOSFET together, and these two MOSFETs actually they are joined together in this fashion. Okay, they are joined together in this fashion. So you have seen that the two MOSFETs which were like single ended joined together at their source and they form a differential pair configuration. So I don't want to go into theory, but yeah, so this there are various advantages of differential amplifier. You must have studied in the class by Sunil sir. So I don't want to go into detail, but I want to concentrate on uh, only uh, the practical part. Practical part. Okay. So what we'll be doing today is, instead of going into theory, okay, we are going to just look at this problem. Okay, look at this problem. This problem is there is a MOSFET amplifier, and for this MOSFET amplifier, you have to first find out what are the condition, DC condition, and then we are going to see the AC condition. So, but our main aim is to find out the DC condition, like what is the VGSQ value, what is IDQ value. Okay, all these thing. Okay, let me just point out on the screen. We will be interested only in some of the value, like this voltage. This is known as VGSQ. This voltage, which is VDSQ. Okay, and a couple of currents, like this current is IDQ flowing here, and this is also IDQ flowing similar, and these two together they come at this point and forms two IDQ at this point. Okay, so this is biased with VDD voltage and this is biased with VSS minus 5 voltage, and there are two input signal applied, and for a differential amplifier they are 180-degree out of phase. So V in 1 and V in 2, okay, they will be 180-degree out of phase in differential mode. In differential mode of operation, okay, V in 1, 2, they will be out of phase. So yeah, okay, let's go and build the circuit in LTSPICE. Okay, so I had shared one video with you people. Okay, did you see that? I have shared one YouTube video with you people. Did you see that? Okay, so let me just tell you in a brief, okay, what we can do with an amplifier. So if you have an amplifier, what three analysis you can do for an amplifier? Any amplifier, whether it is MOSFET, whether it is BJT, so it doesn't matter. Okay, amplifier. Okay, so yeah, you actually do DC analysis. Okay, or you go for transient analysis in LTSPICE. or you go for frequency response, which is nothing but AC analysis. So what exactly are they in LTSPICE? DC analysis will give you all the voltages and current, whereas the next one, the transient analysis, will give you waveforms, sinusoidal waveforms, time based, like on a x-axis there would be time and y-axis there would be amplitude. AC analysis, which is here, actually it's actually frequency response in LTSPICE. The key term is AC analysis, but what you get is frequency response, where your input on x-axis, you will have a number of frequency, and y-axis will tell you what is the corresponding amplitude. So you know that that's Bode plot, something like Bode plot kind of thing. You have on x-axis your frequency, y-axis amplitude. So AC analysis give you a lot of information. This will give you a lot of info. Why? Because this will give you the amplitude, the output for number of frequency. Whereas transient analysis, if you are interested in particular frequency, like how on a particular frequency amplifier behave, then you go for transient. Whereas like suppose for a communication circuit, you must be interested in the number of channels or the number of frequency. So you go for AC analysis. Okay, DC analysis is necessary because you, before amplifier to work, okay, you want to ensure that whether all the voltages and current requirements are met before putting the circuit in actual deployment. Okay, so you require a DC analysis beforehand. Okay, so for any circuit you will be doing that. So let's build the circuit. So I have already built the circuit beforehand. So can you see the so please confirm, one of you, that can you see the actual MOSFET differential amplifier circuit there? Okay, so let's build it together. I will build it. We will be building it together. Sorry. So let's see, new schematic and select components. So we're going to select NMOS. Keep it here. Okay. Second NMOS. So before selecting second NMOS, just zoom out, because we have to fix number of items here. So there is one more NMOS. Just mirror it so that we can just place them one after the other, and then we will require some voltage signal. So yeah, we will require for VDD, we will require one. For VSS, we will require another. We will require for input signal. Okay, and then we'll require a couple of resistors like RD. We'll require RD. We'll require RS. Okay, and yeah, let's fix it. This is here and here. And let's wire them up. Okay, you can just take this. Yes. So this way, and then now there is ground connected. Ground should be connected here and here. Okay. At this point, you will connect this battery. Okay, let's name them. So instead of wiring with the help of wires, okay, what you do is you just give the label. the names. Okay, you connect them by not by exact wires. Okay, just give the name. This is VDD and this portion is VDD. So if you give the same label, they would be connected. Okay, and the next is VSS. Okay, and this would be VSS. And this portion VSS. Okay, and this is VSS. And sorry, at this point, I will just connect a ground here, ground here. This is 5 volt. And this is minus 5 volt. Okay. And this value was 25K. This was also 25K. Give them a name RD1 and RD2 because they are drain resistance. And this is RD2. Okay, this one is RS. Value is 20K. Okay, I think we have set up all the values, and this would be a sinusoidal signal. So I can just select a sine, and DC offset is 0. We can give around 10 millivolt. The frequency we can give you 1000, 10 milli, and delay is 0. We can give theta 0, but we can give 5. We can give so we can give 5 as 0 degree, not a problem. And another, this one we will keep it 180. So this will also will set up now. Sine DC 0. So we will make it minus 10. Why minus 10? Because this is a differential input. So this would be exactly opposite. Delay 0, theta 0, and 5 would be 180 degree. Okay. So in this way, we have this sine 1, sine 2. Okay. And yeah, so like this name given to them is NMOS. So yeah, we can just give them same name, and then we can have here SPICE directive. So we can like give the dot model command NMOS like, and the first is the name, second is the keyword. Okay, and after that you can give the VTO equal to 1 volt, and then KP. Okay, the KP value you can give you 100 micro. Okay, so this, and then yeah, VTO and KP, that would be enough. These two values you have to specify so that MOSFET will have all these values. I think if I left anything, yeah, that's enough. So two values, threshold voltage and KP. Okay, so KN was given 50 micro. So we select process conductance here, KP, which is 2 times of KN. So if you can see that slide, okay, where we have just, yeah, this KN was 50 micro. So in LTSPICE, your KP is 2 times of this. So that's why I have given this value as 100 micro. Okay, 100 micro. So all set now. We can just go and click it, and everything is just a click away. So anybody remember what we do? We do a command. So there are a lot of, like we have seen, like there is a DC AC analysis, there's a transit analysis. Okay, but now we will be going for DC output this point. Okay, So this OP command will be going for, and then we will place it here, OP command. Now when we simulate run, okay, whatever may be the error, okay, the error will be popped up. Okay, so this, okay, before that, going for this, I will just name it v1 and this as v2. Okay, so v1 and v2. So this is how everything is connected. Simulate and we will run. Yeah, before running, there is one thing left. Okay, can you tell me what is that? I have explained that in the video. Okay, so you remember that? If you remember, so yeah, giving the name to the nodes, okay, is necessary. Otherwise, you have to match the, you have to find out which node belong to, what is the name of this node or what is the number of this node. So that is very cumbersome. You cannot, like, finding the number of the node is little bit dangerous. Okay, it's not that easy. Okay, now D1, D2, G1, G2. So at this point, if you need, and you can give another, like you can give S, okay, and you can just give S. Okay, so you can see, we're able to see the value of everything. All the value, you can just look at the values. The drain voltages, the source voltage, and the current flowing is ID. If you see ID, both the value, ID value is 62 microampere. Okay, 62 microampere. So that would be the value of ID. Okay, so this is what we have done, the DSE analysis, and I don't want to go for AC analysis. So that's it for today. This was the last practical, and any query, if you have any query, please let me know.